Hello and welcome to this video on the normal distribution. So everything that we actually learn in this video is going to be really important in our next upcoming video on z-scores. So let's begin with a definition of normal distribution. So the normal distribution is basically a shape that you're going to get from the data. So it says data, when graphed, results in a symmetrical distribution about the mean in the shape of a bell curve. So symmetrical just means it's going to have the exact same shape on both sides. So like this, you can see it has the same shape on both sides. And when it says about the mean, that just means that the center is where the mean is. So it's surrounding, it's on both sides of the mean. And of course, the bell curve, it's called a bell curve because it has the shape of a bell. So anytime you have data that when you graph it, it has kind of this bell shape, we call that the normal distribution. And the reason it's called the normal distribution is because what would normally happen in nature is what's going to happen with the normal distribution. So if nothing affects or alters your data, you're going to get this normal distribution. So you could have, say, weights of infants. So typically there's going to be an average that's going to be in the middle. And then there's going to be some babies that maybe weigh more, but there's less of them, so this is lower. And there's going to be babies that weigh less than the average, but there's less babies that weigh at that amount too. Or you could have, say, the time taken to complete an assignment. Most people are going to be at the average, so this is the highest. And then some people, it's going to take them longer, but there's less people that will take longer. And then some people are going to get it done really quick, but of course there's going to be less people that get it done quickly. And then the last one, heights of students. So there's going to be an average height that everybody's at, and then some people are taller, but there's less of them, and some people are shorter, but there's less of them. So it kind of narrows down on both sides. So what this type of graph actually is here, whenever you have those bars, those are called histograms. And as soon as you draw lines going from the top of the midpoint of each one, that is what you call a frequency polygon. And one other note, in all of the graphs that you're going to have, or all the ones that we see here, the frequency goes on the vertical axis. So that's the number of times that something occurred. So like the number of people with a certain height. And then the range, that's going to go on the horizontal axis. So that's like your data points, like a height of 5'5", 5'6", 5'7", and so on. So some more information that we got here about our normal distribution is this picture right here. So if you were to cut the normal distribution in half of it's going to be on this side and half of it's going to be on this side. So 50% of the data is inside here and 50% of the data is inside here. And then of course the middle there, we said that was where the average is going to be, or another word for average is your mean. So mean had two different symbols. It was this one we called mu, which stood for the total population, or it was this one which we called x bar, and that was for a sample, so just like part of the population. So next we're going to look at some characteristics of a normal distribution curve, and we're going to actually kind of compare it to what we have here. So all data is represented by the area under the curve. So all of the data points, that's going to make up all of this area that's under here. The total area under the curve is 1 unit, or 100%. So if you added up all of the percentages, it has to add up to 100%. The curve extends infinitely to the left and to the right and doesn't touch the horizontal axis. So that's just saying this just keeps going and going and going, but it doesn't actually touch this bottom horizontal line. Same thing going this way. Next, symmetrical about the mean. So that just means it has the same shape on both sides of the mean. And then lastly, E, the mean, median, and mode are equal or close to being equal. So whatever the mean is here, your mode and your median, those will also have the same value. So these last two, these are going to be important for trying to figure out whether something is normally distributed. If you see that it's symmetric or that the mean, median, and mode are equal, most likely it is normally distributed. So next we're just looking at some different characteristics related to standard deviations. So if you had, for instance, one mean, so you had one mean value, they both had the same mean, but different standard deviations, those different standard deviations are going to cause different spreads of your data. So spread of data is controlled by SD, standard deviation. So if you have very small spread or small standard deviation, it's going to be very localized or kind of central. It's going to be narrow. If you have a larger SD, standard deviation, it's going to be more spread out. So it's going to be really kind of wide. You could also have, say, different means or different averages. And your mean, that's what determines the position in the x-axis. So if you had different means, you'd have a mean here and say a mean here. But maybe they have the same standard deviation. That means they got the same spread. So they're going to have kind of the same shape. Now, the only time that this kind of different mean is going to occur is if something is kind of affecting it. So it says it's usually caused by an external force. And an example of that could be like cheating. So maybe you had a test where the people writing the test were cheating. So a lot of them are going to get kind of this higher mark, and they're all going to be kind of localized around that higher mark. And then there's going to be another mean for the people that didn't cheat, and this is where everybody would be kind of localized around. So again, usually that only happens if there's some external force, something that's kind of affecting the data. So now that we've gotten that, what we're going to look at here is dealing with making predictions. So it says if data is normally distributed, you can determine the likelihood that a certain event will occur. So this whole diagram you guys actually have on your formula sheet, but you don't have these numbers right here. Okay, so those three numbers you don't have, but to get those, all you do is just add this up. So 34 and 34 is 68%. So if I asked you, like, what is the chance of something being within one standard deviation? That's what this is right here. It's just over one standard deviation, and then this is down one standard deviation. If I asked you what is the chance of you being within one standard deviation of the average, that would be 68%. So just down here at the bottom, I got it's approximately 68% of the data is going to be within one standard deviation. So one up and one down. If you went, say, 2 standard deviations, so 2 hops, that is going to be 13.5 plus 34 plus 34 plus 13.5. And that is going to give you 95%. So that's how they got this 95%. So that's, again, within 2 standard deviations, 2 hops. And then lastly, if you did 3 hops all the way till the end there, that is going to be 99.7. So that's just taking each one of these and adding them up, and you'll get 99.7. So if you forgot on a quiz, you could just add those all up or just remember these 3 numbers. So the last one there again, 99.7% of the data is within 3 standard deviations of the mean, which the mean is in the middle. So now that we've gone through all that, what we're going to look at next is our first example. So it says, Jim raises Siberian Husky sled dogs at his kennel. He knows from the data he has collected over the years that the weights of the adult male dogs are normally distributed with a mean of 52.5 pounds and a standard deviation of 2.4 pounds. So part A, sketch a graph to show the distribution weights of the dogs. So what you want to do with this, you're going to put the mean always in the middle. So the mean was this right here, 52.5 pounds. So right in the middle, I'm just going to zoom in. We're going to put 52.5, and that's representing pounds. You don't have to put the units down here just because there's not much room for you to fit it in. So to get these other points on our graph, what we need to do is we need to move the standard deviation amount. So I need to add, and the standard deviation was this 2.4 pounds. So I'm going to add 2.4, and when I do that, that's going to get me to 54.9. And then I would continue to do that, so adding it again, I'm going to get 57.3. And then adding it one more time, we're going to get 59.7. So again, this is just continuing this adding of 2.4. To go the other way, you just do the exact opposite. You subtract 2.4. So when I do that, I'm going to get 50.1 for this next one. And then subtract it again, you'll get 47.7. And then the last one, subtracting, we get 45.3. So I've gotten all my data points down on the horizontal part. Then what I'm going to do is I'm just going to write the percentages inside here. This inside percentage was 34%. Same with this one, 34%. Then the next one was 13.5%. Same on the other side, 13.5%. And then the next one, can't really fit it in, but it's 2.35%. And again, same on the other side, 2.35%. And then lastly, the really small one, it's right here, it's 0.15%. And we'll write that on the other side as well, 0.15%. Okay, so zooming back out, we've gotten our graph. We're going to use that graph for all of the parts to the other questions. So part B, it says, what percent of adult male dogs at Jim's kennel would you expect to have a weight between 47.7 pounds and 54.9 pounds? So we're going to have to go from those two different values. So that was from here all the way up to here. And to figure out the percentage, what you do is you add up the regions from one point to the other. So we're going to go from this 47.7 all the way over to this 54.9. So all of this area that's in here, I'm just going to kind of shade it roughly. That is the area that we're looking for. So we're going to have to add on all of those percentages. So I can see that's 13.5% plus 34% plus another 34%. And when I add those all up, you're going to get 81.5%. So it's about an 82% chance of a dog weighing between those two different measurements. Looking at part C, it says, what percent of adult male dogs at Jim's kennel would you expect have a weight of between 50.1 pounds and 59.7? So again, I'm just going to go back up here. I'm going to erase the area that we had highlighted for that one. And now we're going to go from 50.1 to 59.7. So we're going to start at 50.1 and we're going to go up to 59.7. So that was right there. And again, I'm just kind of shading rough just for you guys to kind of see the area that we're doing. So I can see there is a 34, a 34, a 13.5, and this spot right here that was 2.35. So let's add those all up. So that was 34 plus a 34 plus 13.5 plus 2.35. And when you add all of those up, you are going to get 83.85%. The last one here now, part D, it says, what percent of adult male dogs at Jim's kennel would you expect to have a weight less than 45.3? So let's go back up and we have to be less than 45.3. So I'm going to erase that zone that we had. And now we are less than 45.3. So that is right here, less than 45.3. And that percentage is just 0.15%. So that one I didn't even need to add anything up. I can just see that it is 0.15%. So our answer, 0.15%. So that one's all done. Now we can move on to our last example here. And it says, Shirley wants to buy a new cell phone. She researches the cell phone she is considering and finds the following data on its longevity in years. So all of these values are just years that a cell phone has lasted. So 2 years, 2.4 years, 3.3 years, and so on. So part A, it says, does the data approximate a normal distribution? Why would it be important for Shirley to check this? So let's answer this first part. To figure out whether something is normally distributed, we had said on our first page there, if the mean, median, and mode were close to the same value, or if it had kind of that bell shape, then it was going to be normally distributed. So what we're going to do is we're going to calculate those and see if it is normally distributed. So in order to calculate the mean, median, and mode, I'm going to have to take all of this data and put it into my calculator. Now you could take all of these numbers and just punch them in, but that's going to take a little while. So what I did was I wrote out just each number once, and then I made a frequency table for how many times it repeated. So like 3.1 is here, and it's here, and I counted up how many times I got that value. So I've already created that, and that is this table right here. So what we want to do is we're going to enter all of this information into our calculator. So I'm going to pull out my calculator, and to enter in our data, we need to go to Stat. So you're going to click Stat, and then you are going to click Edit in order to make your list. Now I've already put in all of these years into my list 1. So I've got all my information already in there, and my frequency, I've already put all of those values into my L2. You just got to be careful that you make sure each one is across from the correct one. So once we have all that, to calculate the mean, median, and mode, you're going to click Stat, and you're going to do Calculate, and then it was 1var stats. We went through this in our last video. And then our information is in L1. So L1, we have that in. Our frequency list, I had put that into L2, so that's good. And then I'm going to click Calculate. If you had the older TI-83 calculator, rather than it taking you to this screen, it took you to the main menu, and then you just had to put in L1, comma, L2, and then enter, and it would give you the same thing as what this is going to give. So I can see with this, I got my mean, that is right there, 2.526, and I can see my standard deviation. Again, it was for a sample of cell phones, so it's this 0.4868 number there. And if I scroll down, I can also see my median is 2.55. So I'm just going to scroll back on our page. And what we wanted to do is we needed to calculate the mean, median, and mode in order to see whether it was normally distributed. So I'm just going to write that down. So in our calculator, when we found our mean, remember x bar stood for mean, we got 2.526. Our standard deviation, we got 0.487 when you rounded it. Again, I'll just bring my calculator back out and show that. So it was right here, 0.487. We're using this one, the S of X, because this is a sample of cell phones. It's not all of the cell phone data, right? There's a lot of different cell phones. It's only a sample of them. And then again, our median, that was right here. That was 2.55. So let's write that down too. Median 2.55. Now, if I look at the values that we have there, the mean and the median are really close to each other. So if those were close, that is kind of one hint that's going to tell you that it is probably normally distributed. So I'm just going to write that. So the values are close, therefore it's going to be normally distributed. The other way that we could check and see whether it was normally distributed was by looking at the graph. So I'm going to show you how we can get the graph. What you're going to do is you're going to click second and then y equals. That'll get you to stat plots. So once you're in there, click enter on the first one just to go into a plot. And then you can turn it on. And then you can pick how you want it to look like. If you want it to look like a histogram, you can click histogram. And then you can go down to X list and you're going to put in L1. That's where we put in our information. And then our frequency, we put that into L2. So we're going to put in L2. And then once you have all of that, you're going to click graph. Okay, now my graph, it didn't show up very nice just because of the window. So I'm going to go into my window and I'll change my window. None of my points, none of these here were negative, so I don't need to be in the negative. I'm going to change this to start at 0. My X max, the largest point that I had was 3.7, which is right here. So I'm going to go a little bit more than that. I'm going to go up till 4. My X scale, these are down to the nearest tenth. So I'm going to go up by tenths. So I'm going to go 0.1. My Y min, this deals with the range. So none of these happened a negative amount of times. They all happened at least one time. So I'm going to start at 0. And then the Y max, the most that a point actually occurred was 2.7 was 6 times. So I'm going to go a little bit more than that. I'm just going to go up to 8 just so I can see everything on my graph. And now that I've got that, if I click graph, now I get a lot better picture and you can see it has kind of this bell shape to it. So if it has this bell shape, then it's going to be normally distributed. So let's write that. So we've answered most of part A now. Just the last thing was, why would it be important for Shirley to check this? So this would be important so that she knows that this cell phone follows a normal distribution so that you're not going to have maybe the odd cell phone having a really, really short battery life. If they all kind of tend towards the middle, right, just pulling this back out, if most of them have kind of this average battery life in the middle, then you're maybe not going to get a cell phone where the battery life is really, really poor. On average, they all have kind of the same amount of battery life. So moving to part B here now, it says, if Shirley purchases a cell phone, what is the likelihood that it will last more than 3 years? So first thing we're going to do is we are going to, like in the last example, draw our information on our normal distribution. So the mean was this, 2.526. So we're going to put that in the middle here, 2.526. And then to get to the other points, we're going to have to add or subtract the standard deviation. So I'm going to have to add on 0.487. So 0.487. When I do that, that is going to get me 3.013. And then adding it on again, I'm going to get 3.5. And then adding it on again, I'm going to get 3.987. Okay, going the other way, you're going to have to subtract that 0.487. So to get the first one, after we subtract, you'll get 2.039. So that's 2.039. Next is 1.552. And then the last one is 1.065. So now that we've got all that on our normal distribution, we can answer the question. So it had asked, what is the chance that it's going to last more than 3 years? So on our graph, there actually isn't just the value 3, but there's one really, really close to 3. So that's what we're going to do in our next lesson actually, is when it's not precise like this. So for today, we're just going to round it and get close. But in the future, if it's not precise, what we're going to do is we're going to use z-scores, but we'll see that later. So for now, we're just going to do it close to what it should be. So again, it asks for more than 3 years. So if this is at 3 years, we want more than that. So if I highlighted past 3 years, that's going to be all of this here under the curve. And writing our percentages in there, remember this one was 34%. Then this next one was 13.5%. And then the next was 2.35%. And then the last really tiny one is 0.15%. So I'm just going to add up all of those highlighted regions that we had. So it's going to be 13.5% plus 2.35% plus 0.15%. And when I add those all up, you are going to get 16%. Okay, and this one is approximately equal to 16%. Because this wasn't exactly 3. So looking now at part C, this is our last one. It says, if Shirley purchases the cell phone, what is the likelihood that it will last at least 18 months? So now the problem with this, if they say 18 months, all of our information was given in years. So I got to change 18 months into years. So I know that there are 12 months in a year. So I'm going to use that to convert this. So in 1 year, I know that there are 12 months. So I'm going to multiply by that, and that's going to convert this. So I'm going to have 18 times 1, and then divide by 12. So 18 times 1 is 18, and then dividing by 12, that is going to give us 1.5. So this is 1.5 years. So on our graph, 1.5 years, the closest one is this right here. So we wanted to find what is the likelihood that it will last at least 1.5 years or 18 months. So we want at least that and then more. So we want all of this region. So I'm just going to erase what we had highlighted before. So we want at least from here all the way up until its max battery life. So all of this right here. So what I could do is I could add up all of these regions, and that could get me my answer, or it might be quicker if I just took 100% and I subtracted out this region and this region. And those two regions were, that one was 2.35%, and then this really, really tiny one here at the end, that one was 0.15%. So I'm going to take 100% and then subtract off those. So 100%, subtract off 2.35%, subtract off 0.15%. And when I do that, I'm going to get 97.5%. And again, this is approximate because this value, the 18 months, was 1.5 years, and I don't have exactly 1.5 years. So this is just roughly close. In our next lesson, we're going to do z-scores, and it'll get it even more accurate. So lastly, I'm just going to write our textbook questions here now at the bottom.